As we were saying last time, we are going to close the subject of wood, and we are going to introduce composites. Some last observations about wood. Wood is typically, in most cases, a laminated structure. So you might have some solid wood, especially in furniture, but in most cases you have laminates. Laminates, that means basically that you have some layers of material, which in case of wood have got fibers. And so you have fibers and the matrix, which is the softer matter in which the fibers are inserted. As a general consideration, fibers take the tensile load. So if you want the material to withstand also some tensile load, you need to have fibers as long as possible. Okay, and then you have some layers of materials. As you may remember, wood, especially solid wood, is particularly loaded in bending, in flexure. So that's the way in which it is tested usually. You have these laminates, and well, you have this already some slides the last time indicating the different types of laminates. You may have chipboards, basically with short random fibers. When I say random, I mean that the fibers are in whatever orientation. We are not able to say what they are. We assume they are roughly in all directions, 2D sense. Then there is the question of thickness. Thickness is a big problem because you may need some thickness in order to get some resistance. In other sense, it's a problem because you need to have laminates with a number of layers. Number of layers which are put together with two procedures, basically. I try to keep as simple as possible that. So by pressing them or by gluing them, so applying an adhesive and put the layers together. You may easily understand that in terms of end of life, laminates represent a problem because you might have an adhesive, which is usually a synthetic adhesive, an adhesive that works particularly well with wood is vinylic. So the material which gave rise to a particularly well-known type of plastic, which is polyvinyl chloride. And you may have even bonding, therefore adhesion and pressure together. So first an adhesion, then you complete the process of making a structural material, so a material which is able to get some load in applying some pressure. Of course, you are limited into that. The pressures are not as high as it will be the case with polymers. The pressures are quite low because otherwise the material will not withstand that pressure. And also you have basically a solid material, and so you press that amount which allows you to make it as one structural material. Another big question is to get a curvature, because you can get a curvature from wood just by material asportation. So you might have, for example, turning in wood, which is a typical operation, and then you get some curvature. More recently, I'm saying in 1850, so not in ancient times, we have had curvature, which has been developed, the curvature, by the application of vapor, of water vapor. So high temperature vapor or low temperature vapor. Or you can have even a cold pressing like this chair, which was developed by Marcel Breuer, and you have seen thousands of imitations of that chair. It was in the 30s, 1930, around 1930, 35. And from that on, we had had a number of imitations, because it is a clever way of curving wood without applying a high temperature. The process with high temperature, with vapor pressure at high temperature, was known from 1850 by Tonnet, which was in a craftsman in Vienna, and developed this kind of chair, which was particularly good and imitated as well. Okay, so in practical terms, what you have in wood, you have this kind of sandwich structure. Sandwich structure means that we have two layers on the outside, and which are called skins, and a bigger, thicker layer, or a combination of thicker layers on the inside, which are softer and which are called the core. Then, in terms of damagement of this material, you have an application of force. Then you might have the core breakage, which is due to very high forces, that you may understand. In other cases, you might have the straining, so you have the skins which are yielded, so they get up to the elastic limit and over that, and in fact they deform in a plastic way. You can find a lot of examples in home, for example. Or you might have an adhesion fracture, so the glue doesn't withstand the load anymore, possibly because there is some moisture entering, or there is a non-uniform and uneven load, and so on. Then you can have the skins, something which affects the skin. The skin might buckle, so have a compression, an uneven compression. We call an uneven compression, not a flat compression, but an uneven compression. So with a force which is not straight force, it's an oblique force, and therefore you have this buckling. Or you might have a penetration which is even worse. So you might have a compression which leads to the fracture of skin by shear, not by compression, by shear. So it's not a core breakage. You have a shear fracture which leads to a kind of partial penetration. Here I repeat the types of materials you have. You have the medium density fiberboard, the higher density fiberboard, chipboard, etc., blockboard, and the plywood, which is very diffused with some veneers on the outside. And then you have a number of layers with different orientations of the fibers. With different orientations of the fibers. This is important. That's what we want to have. Why different orientations of the fibers? Because you may easily understand that since fibers take the tension load, if fibers are all in the same load, in the same direction, which might be done, it's called a unidirectional material, then you are able to withstand the tensile force only in one direction. All the other direction will be weaker. Um, Having the fibers at different orientation for each layer means that in the end you have a sort of balanced withstanding of the force on the 2D, on the plane. So basically, it's withstanding the load in mostly in the same way and with the same resistance in all directions to the end. This is the model, of course. From the model to the reality, there is still some difference. It is interesting that in case of wood, we passed from craftsmanship, which was the one I was mentioning with Tonet, to the industrial production, and therefore some simple solutions like this one, the vapor wood curbing system with a flexible supporting steel. You know, we are in 1850, and so there was no problem to make some flexible supporting steel. With cast iron, it wouldn't have worked because also it would have been very heavy, and also it would have been not very um, tactile. So in the end, you need some elastic deformation, and because you need to adjust the clamp and to be able to the, curve the wood. So you put basically the wood against the flexible support, and you, you restrain into the desired shape. This has become also very, in the recent years, it has become also very flexible, this kind of production, and also together with cold pressure. Now pressure can be applied also here at cold from Breuer's time. So there are a number of options into the curvature of wood. And this is not the only way in which we can apply pressure on wood pressure and addition to wood, because so making one structural material, just one structure. There are lots of join. Wood junction is a fascinating word, and you might have halving joints, doublet joints, and so on. If you look at IKEA catalog, you will find all of these solutions and also some more solutions, depending on what you want to do. And in practical terms, what interests us is that any solution gives to us a different arrangement of forces. In some cases, the forces are more evenly distributed. For example, the dovetail works very well because the forces are really very well distributed, especially if you have a kind of outline or dovetail. So the forces are evenly distributed on the whole of your joint. Even box joint work very well, and it's simpler than dovetail. It's simpler because you cut straight and you don't cut at an angle. Cutting at an angle, it's more difficult. In some cases, you have to put reinforcement, like with dowels, like with dowel pins and with brackets, etc. So this gives you an idea of what can be the complexity of situation in these natural materials. There is not just one way of connecting materials. We didn't talk in our course of welding of metals. I may have a return to welding in the last lecture, just because it was important, but as a matter of fact, you find that um, welding can be done in just a few ways. In this case, instead, you have a number of different solutions to try to make the different laws even. And of course, there is also another question. Do you want movement, any kind of small movement between the pieces of the joints, between the parts of the joints, or do you want to avoid movement within the different parts of the joint? This is another question that orients your choice about how to put together the different parts of the wood to make joints. You might put nails, you might put screws. Screws are adjustable, nails are not, which makes already a difference. Dowels allow some small movement, less than the movement allowed by screws, but more than the movement allowed by nails, which is basically no movement at all. So this is important for us because material science is also a question of how to withstand the loads and in which way to adapt to our materials. Then there is, especially in the last few years, there is the question about end of life. End of life means that I am supposed to disassemble all these loads. For example, all these joints. For example, if I didn't use any glue, well, here we suppose that we are not using any glue. In some cases, we use glue. If we use any glue, then I would be to remove the glue. I need to remove the glue, which contaminates wood at end of life if I want to recover wood. Even for incineration's sake, even if I want to have the so-called energy recovery of wood, then I need to remove them, the glue, the adhesives. If I have nails, I might remove them. If I have screws, I might easily remove them at end of life. And the screws will go into metal and wood will go into general waste or reduce it into chips and making other wood. Please remember that wood is a thermoset. Thermoset burn, whilst thermoplastic soft. So end life options are introduced, have been introduced recently, which complicate further the matter because we have to select materials and for load application, of course, for service, of course, but also in order to be disassembled, so separated at end of life. The example I was making, it's a kind of self-assembly. I put screws into metals, I put wood into wood, and I remove glue as much as possible. Otherwise, wood would be contaminated, and I am not able to use it, for example, for energy recovery, and either even less for recycling, which in wood means mechanical recycling, because in thermostatic materials, since they don't soften, the only recycling that can be done is mechanical recycling. So I grind everything and I put into something else. So from wood, I'm quite smoothly, I'm going into composites. When I talk, well, we have already talked a bit about metal matrix composites, so kind of aluminum particles or magnesium alloyed with magnesia particles. So we have metal matrix. The matrix is bulk of the material. Then there is a reinforcement or filler. The difference is not academic because reinforcement reinforces, or I can have a filler with just modify something else. For example, in polymers, I might have a filler, I might have a calcium carbonate, which doesn't reinforce the polymer for the way it hardens the polymer, but it doesn't reinforce the polymer for the way which I have to use the polymer for. If I want to make a whatever container into plastic, I would say that the addition of ceramic would harden a bit the polymer, would allow the polymer to flow better, but in a more controllable way better. But on the other side, it would not making it stronger because polymers work, well, don't work into compression usually. They tend to work into tension and sometimes into bending, but ceramics don't give us much strength into that, just into compression. We already talked about ceramic matrix composites like concrete. Concrete is ceramic or reinforced concrete. So we have the cement, we have sand, gravel, and so on, and we have steel bars, or steel extruded bars, or a steel net, which are inside our concrete, and make it a ceramic matrix composite. Here we are talking, therefore, about the third type of composite, which is polymer matrix composite, and wood can be assumed to be a polymer matrix composite because it has a softer part and it has a stronger part which constitutes fibers. We may roughly assume that fibers are mainly made into lignin and the softer part are made cellulose, which both are polysaccharides, cellulose and then cellulose, but cellulose is less old than cellulose, although both are amorphous. Fiber reinforced polymer composites. What do I need to do? I have a matrix, which is polymer, and I have fibers. Usually I take this kind of fibers. Well, these are the 80% of the market, it's glass fiber polymer composites. So fiberglass, the so-called fiberglass. And most fiberglass, it's with 80% of that 80%, I would say, it's made of thermoset, because there are some fields in which, as I have said already a number of times, which don't allow you to work in temperature. This is the shipbuilding, the building field, and also other fields like in automotive, in most cases in automotive, and therefore I need to use thermosetting matrices. Although I know also that this is going to be difficult in some cases because you understand that end of life. At end of life, you know, thermosetting materials are not able to be recycled. Okay, and what do we need to obtain? We need to obtain fibers which are completely covered. Their outer surface needs to be completely covered into with the matrix, with the polymer, and this means one other thing that I don't need to have resin pockets. Resin pockets means that places where there is just resin, and the fiber needs to be completely wet, completely impregnated, that's the word, with resin on the outer surface. This involves another number of questions. I need not to have air bubbles. And and that's another matter because air bubbles are weaker parts. Then there is another question as well, is that in some cases I need to join. You may remember joints because we talked of them in the last slide. Well, here junctions are, especially thermosets, are much more difficult to make in a repeatable way because they are basically made by hand. And basically because I have a lot of trouble in cutting, for example, glass fibers or carbon fibers. In polymer joint, in composite polymer joints, polymer composite joints, I need to have some resin pockets in cutting some layers of fiberglass and trying to make them suitable with not much of air bubbles and air entering. So I might try to do something making a void. There is a kind of vacuum, the so-called vacuum bag molding, so I can make some void. I cannot rise that much in temperature, but I can try to make vacuum, so to avoid air entering. Not a complete vacuum, but to reduce at least the pressure with respect to air pressure. So, well, 80% is glass fibers. 80% of that 80% around is thermoset polymer glass fibers, fiberglass. The so-called, usually fiberglass is referred to thermoset polymers with glass fibers. Then I have for high profile applications carbon fibers in the automotive, in the aerospace, in the military industry as well. I have carbon fibers or aramid fibers like Kevlar fibers. We are called Kevlar fibers. Most recently, I have introduced also some other ceramic fibers which are competitive with glass, which are basalt, and they have quite some market. Still a few percent, but they have some characteristics which are interesting, especially the fact that they need less treatment and less production cost than doing glass fibers, producing glass fibers. Also, I have vegetable fibers, the so-called lignocellulosic fibers. So the fibers which are basically taken from plants. This is a field I have been a lot involved in, the production of natural fiber composites. For example, hemp, for example, flax, for example, coir, which is coconut, etc. I hope to be able to say something in the last few lectures. Although the subject is very interesting because it makes the material more sustainable and because it's able to exploit competencies which are well known in other areas like the textile. So, as you may understand, composites can be broken, can be damaged in different ways, can lead to fracture in different ways. You might have the fiber fracture at high loads, or you might have matrix tearing. The matrix is torn, so in shear shear basically. You might have the fiber pull out, so the fiber pulls out of the matrix. They separate, so the interface, we call interface the surface of separation between the fiber and the matrix. And we, the composite will work in case fiber and matrix are well bonded, and this is called the interface strength. If the fiber pull out, means the interface has broken. Or you might have a matrix deformation. Remember that matrix is a polymer. That means that it might undergo plastic deformation even at very low load. We are going to talk about polymers in the next 1 or 2 lectures, and you will have more information about that, but please be aware that polymers might be plastic even at very low deformation. And then you have the delamination. Delamination means that you have layers, and layers tend to detach from each other. As it happens in wood laminates, it's a frequent occurrence that, for example, water penetrates and the layers are detached from each other. And possibly the thickness appears to grow, but the structural force is low. So this gives you more information about the fibers, because the fibers might be continuous. We are going to say what this precisely means, but in general terms, continuous means that you have, for example, a wave structure like a tissue, a fabric, and or you have unidirectional long strands of unidirectional fibers, like it is often the case with, for example, with carbon fiber composites, or you might have short fibers, or you might have even particles. In some cases, you might have particles. Particles in most cases are fillers. You might have fillers, and in some cases, this is still used quite a lot. They more behave as fillers. Among the strange things I have done in the last few years, for example, I have put some powder of licorice root into an epoxy resin to see what was happening, because it was a waste, and it's good to reuse a waste in many cases. But you can easily understand that the reinforcement that you obtain with particles is not that amazing. You make the material cheaper, harder, but generally speaking, not stronger. Not stronger in tension. It might be stronger in compression, for example, because they are no longer fibers, so basically they are spherical, sort of spherical. You need you need to come out of the theoretical physics approach. Well, it is always an approximation. It's always a model. I am not saying that particles are exactly spherical. They tend to be spherical, or at least they don't have a length which is considerably larger from diameter. An important thing, we call the to diameter ratio the aspect ratio. Therefore, it's the ratio between the lengths and the reinforcement of the fiber, of the particle, etc. As always, probability distribution of the aspect ratios, for example. So you have a number of different situations. You might have some fillers, flakes, particles. There are some subdivision. For example, I may say that if they are more spherical, they are called particles. In other cases, they are called flakes. Or you might have a kind of elliptical shape and they are called fillers. Then you might have a number of which might have all the same orientation. so you might have a unidirectional. You might have a bidirectional. A bidirectional means that you might have some fibers oriented in one direction, and the following layers as fiber oriented at node 90 direction. So the so-called node 90. That's what engineer prefers, node 90. No much difference in what you see in wood. Then you can have mats which are not exactly, they are produced by punching, by being punched basically. So they are not, you don't have a real wave structure. You may imagine mats. Easily think of your door mat, the mat most people has on the door. This is a mat which is not an issue, but it has been punched in a way that the fibers stay together. But of course, they have a random orientation. If you look at your door mat, you cannot say that the fibers go on the same direction. Then you can comb them and allow them to go rather to some directions you more like. Okay, here I am showing an example of one of the attempts which has been done in the last few years, because in the last few years we try to replace the thermosetting, this traditional thermosetting polymers, which we cannot get rid of because it's important to be able in some fields to work at room temperature, with some bio epoxy, for example, biothermosets, which are obtained, for example, from some kind of plant oils as soy oil. And since we have done all these effort, then we suppose also to put some, in that case, we suppose also to put some natural fibers like hemp fibers. And you could have a coupling agent, because the problem with natural, what is the problem, main problem with natural fibers? If you know anything about chemistry, you would know that the similar, a similar substance is compatible, two similar substances are compatible. So in terms of solution, of chemical solution, but also in terms of material, that they bond together, they stick together if they are similar. One of the main classification into engineering and in general terms in physics is between hydrophobic and hydrophilic materials. So hemp is going to be, come from a plant, is going to be hydrophilic. A polymer, an oil-derived polymer like epoxy, like epoxy resin, is going to be hydrophobic. They are not going to play well together. They are not going to bond well together unless we put something which is in between, which is less hydrophobic than epoxy and more hydrophobic than hemp. So in the end, a kind of hybrid, a kind of hybrid behavior, a kind of coupling agent, which is in this case, for example, is the methacrylate isocyanate. There are some kind of methacrylate isocyanate which can be obtained also from some natural materials, some natural, so they are bio-based. We are going to discuss that, but now there is a lot of discussion about biomaterials, and biomaterials are biocompatible materials. Materials, then you have bioplastics, which are plastics of biological origin, and you have bio-based plastics, which are plastics which are obtained from biological materials, but they are the usual plastics. So, for example, you have polylactic acid, which is obtained from corn starch, and it is a bioplastics. And you have bio-based plastics. You can have biopolyethylene, which is, for example, obtained by residues of sugar cane, ethanol from sugar cane, and this is still the good old polyethylene in a sense, like the one obtained from oil, but it is no longer obtained from oil. So you might have new plastics obtained from biological materials and old plastics obtained still from biological materials, but behaving as petroplastics, as material obtained from oil. We are going to discuss that later on. Don't worry if you don't grasp all the details of that, because the matter is very complicated. And it's complicated further by the media, which says whatever they think, giving sometimes not precise information. Okay, so this is a kind of situation, some of situations which you can encounter. For example, we can have a carbon fiber braid. Braid, it's a way of arranging fibers into a wave. Because if we want to move away from random fibers are nice because in principle you have a 3D kind of isotropic. You may think it is isotropic. In reality, it's not isotropic because it's a composite. So two materials together, bonded together, hopefully. But in reality, you are not able to control the direction of the fibers. So it's not isotropic at all. It's simpler, especially working with waste. It's simpler to put, if you have some old glass fibers which you want to recycle, you try to remove the resin if you, as much as you can, and then you chop everything and you put into a new material in random because you don't control anything really. But of course, the performance is much lower. Performance, it's obviously much lower, and you cannot guarantee, for example, a tensile strength in one direction or two directions. So you want to make a wave structure, and you resort to the experience you made with textile industry. Textile industry has a very long history, and you are able to use some of this experience in terms of looms, in terms of way of arranging fibers. And one of the examples is braid. Another example is stitching. Why do you stitch something? So you take a needle and a wire and you stitch. You stitch in clothing, in textiles. You stitch something when you want to ensure some resistance also in the thickness direction. You want the tailor knows that he or she needs to stitch if he wants to, for example, to apply a button. And to apply a button, we need to provide some resistance also on the Z axis, or to keep two layers of tissue together without gluing them. You need to stitch, and the stitching is applied also into. For example, this is a mixed glass Kevlar weight. And because and one thing I didn't say, but it's obvious that you have these possibilities in terms of fibers, and you have all the possibilities of hybridization. So I can put two or three of these fibers together. Of course, I increase the complication of the material, but there might be some reasons, for example, to put fibers together. Also with natural synthetic, there are a number of studies, for example, of glass flax, glass hemp, because I make fiberglass more sustainable, or I might have connection with textile industry, and I might have for free some flax, some hemp, and so on, some wave, and etc. Um, in practical terms, in some cases, I am not able. I don't feel as confident to just put some glass, sorry, hemp or flax, and I put together the wheat flax in an hybrid, and so I will be more confident. Then I need a way to measure the number of fibers which I have in carbon fibers. This is very critical because they have also different prices, different performance, etc. The number of filaments, here you see in the braid, you see the filaments are the small ones that constitute the part of the braid, the fibers that enter up or down into the braid. So I may say that, for example, carbon fibers, which are 1K, have 1,000 filaments constituting a single fiber. So this is another requirement. So the filament is the technical fiber. The technical fiber is the smallest unit that allows the material. Consider that in natural fibers, what happens is that the nanomaterial, so in practical terms, the filament is the smallest wire on which I can work. But in reality, the material can be so also as a nanomaterial because that filament is constituted by thousands or millions of micro and nano fibers, which is not the case for carbon, Kevlar, glass fibers, where I can really produce the single filament and then put together into a fiber. But I cannot go below the single filament unless I do some procedures like for it was the case for the production of graphene, where I really build the nanofiber from below, from assembling carbon atoms. And these are some of the ways of arranging these weave composites. So I might have the typical textile structure, the 2D with warp and weft, or might have a braid. I was already saying that. I might have a stitch if I want to have a third direction resistance. I might have a diagonal stitch, a V stitch, the X stitch, and so on. I make an assumption which is important from your point of view. It might be not, but it is. And I am assuming making a very strong assumption that the fibers are cylindrical, which in most cases they are not. They need to be prepared to become really cylindrical. And why so? Because if they were really cylindrical, I would have a predictable amount of voids in the wave. Since they are not completely cylindrical, there might be some variation in the amount of voids I have in the material. Voids are important because if I have to put them into resin, then the amount of resin I put changes, and the availability of a good phase also might not be always sure, because I might have voids means that the resin can be penetrated better in some places, not so in other places, and therefore I need some adjustment, I need some treatment in some cases. In natural fibers, in lignocellulosic fiber, I may need definitely some treatment. So my idea is always to have an isotropic material, but it's a mess. You may understand that, well, isotropic material, well, they are not that interesting for composite, but at least I would like to have a 2D kind of isotropic material, which stays together also on the third direction. So I might provide it with some good bonding, or even with some stitching if needed. Of course, bonding, as you may easily understand, from an industrial point of view, bonding is much simpler than stitching. That's why you don't find many tailors around, because stitching something that the industry doesn't like that much to do, because it's a reasonably complex matter, whilst bonding is not that complicated. But stitching is much more reliable in another sense. So I have a number of situations. This is a model, which is the way that commonly the layers are put together. So I might have an angle Y, for example, plus minus 25 degrees, plus minus 45 degrees, and so on. And I have some particular situation. I might have a note 90, the cross Y, or I might have an any angle Y, so plus minus theta angle. Um, I can have a completely anisotropic material, which is not usually the case, because I tend to try to give to the material some kind of quasi-isotropy. The quasi-isotropic is note minus 45 plus 45, 90. So this is the orientation of the fibers in every single layer. Consider that in glass fibers are thicker than larger diameter than carbon fibers. When I say larger diameter, I mean 25 microns per filament. And in reality, what you find out is that you can pile up a number of layers, you can lay up a number of layers, and you can make, usually you make a number of layers which is a 4 to some power, so it's 4 or 4 multiplied by, needs to be a multiple of 4, even better, a power of 4. So if I have 16 or 16 layers, it's one of the common situations, but 8, 32 layers are also common situations into carbon, especially in glass fibers, since they are a little bit more less technological in a sense. You may find some other kinds of numbers of layers, but and usually lower. You never get to 32 layers of glass fiber composite. You may stick to 6 or 8, something like that. But apart from the number of layers, it is important that if you are not able to obtain a quasi-isotropic to control exactly the direction, because you may you may think that it's easy to control the orientation of the fibers, but in reality it is not, because if you think of textiles, even with a good loom, it's very difficult to control exactly the angle of the fiber. At least what is important is at least to have an orthotropic material, so a material with constant properties along each one of the main directions. The effect the effect, the way of layering these materials is usually neglected in this kind of models. But of course, there is still the influence on the way of production of composites. Next time, I will try to give you more details about the way in which we produce this kind of composite. Also, because there is a kind of superposition between what we do on composites and what we do on polymers later on. And this has an influence, the process has an influence on the availability of the heat. We tend to think that at least they are orthogonal, so in every direction, we can say that in every point, in any single direction, they have the same properties. In particular, they have the same tensile strength and tensile modulus. So Ashby again, what does Ashby say? Well, of course, the density is around, thinking that carbon fibers are around 1.8 of density and glass fiber 2.5. Kevlar is less than carbon and natural fiber are even less again. And you can put 50%, 60% of fibers into a polymer. So in reality, the density it's around a little bit more than one, between 1 and 2 in most cases. Here, there are some examples are made. What is important is that in some cases you have carbon fibers that they may grow of orders of magnitude, since they are produced in an energy intensive way, and basically they are produced from graphite, but they can be refined and also treated in order to get to a precise diameters and so on. Precise diameters means that you can have a much stronger and a much stiffer material. So they might have Young's modulus. You can get values which are much higher than those for steel. You might have carbon fibers with 700, 800 gigapascal of Young's modulus, which is 4 times more than steel. On the other side, they are brittle, but we put many fibers together into a composite, so it's no longer a question of thinking about brittleness. They still are brittle, but that's the way they work. They absorb also a lot of energy in damage, which is important in some cases. Think of racing cars, for example. In the case of an accident, you can see that they absorb lots of energy, which means that in fact the pilot is no longer wounds and so on, no wonder, because the car has absorbed most of the energy which is developed in the accident. As a matter of fact, in most other cases, glass fibers are used because they are less expensive. So you might have high modulus, very high modulus, ultra high modulus carbon fibers. You have aramid fibers, which are Kevlar. You have also another pattern, which is the quaron fibers. But apart from that, you can see that the question is having stiff materials with low density. Whilst in the case here, it's a logarithmic scale, you can see that the polymers have got a few gigapascal Young's modulus. Here, the natural materials, for once in a while, they are not considered. Usually, Ashby considers always natural materials. But we had already seen the specific diagram. So, if you want to make some calculation about composites, what do you do? In practice, there is a very simple rule, which is the rule of Mister's. You can see that it's really very simple. which you can use for stiffness. Here is where here is what I show, but you can use this also for strength. You can use it for basically any thermal conductivity, whatever. The idea is that the composite materials behave according to the amount of the matrix and the fiber I amounts which are calculated in volume fraction. Having said that, a rule of Michter's works making a large number of assumptions. First of all, is that think of tensile test. I don't move that fast. Time makes a difference because you might easily understand, you may remember creep in metals. We have creep at high temperatures. So creep is the influence of time over mechanical behavior. In the case of polymers, polymers have got creep also at room temperature, at low temperature, etc. So I make a number of assumptions which are not in any sense, but they are useful to make calculations. So I don't put that fast, and this I can do. Of course, this is good in test. I cannot know whether in service a fast tensile load occurs. So another assumption is that there is perfect bonding between the fiber and the matrix, and you can imagine how this can be true. This is far from true. The fibers can be long and continuous, needs to be long and continuous. This is, well, this can be done because I can manufacture the material as I want. And volume fractions are constant in their whole structure, which it's roughly true for carbon fibers. For glass fibers, it's already not very realistic because I might have a resin pockets, etc. Because it's a bit of more a mix match fabrication of fiberglass composite that is the case for carbon fiber composites. For natural fiber composites, it's a complete mess. Structure will be never constant across the composite. So how do you use rule of Mister in practice? Rule of Mister's gives you the maximum possible properties, volume properties that you can achieve. Then you need to test them and you see how far from the rule of Mister's. There are also a number of other models that assume either that there are voids, either that there is no perfect adhesion, etc. I don't go into details about that because this would involve. But the rule of Mister retains its importance because it gives us the heaven situation, the best situation I can imagine in composite. And it's important to know how far you could possibly go in using in fabricating your composite. Oh, so here you can see some other. You can see some other cases. Just a few more minutes. For example, here there are some examples. Sorry, this is still Italian because it was a previous Italian slide, but I will correct for putting the slide into the site. And in practical terms, here we have a number of areal weight. How do you measure that? You can measure by the filament number of filaments per fiber, as we were saying before, for carbon, but you can measure them also in very simple terms in areal weight. So, for example, you can, well, areal weight is simple because you measure the weight and you divide by the area to measure the weight of 1 square meter, say. And so we can have a number of different ways to arrange them. Plain, twill, and satin, for example, the typical examples. The tissue, non-tissue, which is very diffuse. Now we are talking a lot about tissue, non-tissue. Because one thing I didn't say is that we can put a resin, but we can also put some layers of glass fibers with some layers of, say, polypropylene, and then stick together in a polypropylene matrix. We have a chopped strand mat, which is in glass fibers, and basically they are put together by a punch into making they are pre-impregnated in a sense with the resin, so they are put all together. And flax, this is for example flax, and you can see that the bolts are not controlled. But this is very interesting. This is a field I am very fond of, natural fiber composites. And they have some potential to substitute in some cases glass fibers, not so carbon fibers, which are included, which have a different value. Other variables, there are other variables, the so-called mesostructure. The mesostructure is what is in between with the macrostructure, with the structure of the whole composite, and the microstructure, which is the structure at the level of a single fiber adhering to the matrix. So in practical terms, I can you may remember in the last slide I was showing the tissue, non-tissue. If you use a tissue, non-tissue, and then use glass fibers, and then you put all together with resin, you bond everything with resin, you have polypropylene fibers, which are the elliptical one to the right, and the cylindrical glass fibers. You have, you can see here also some bolts due to some glass fibers, or some polypropylene fibers. Pulled out during fracture, and these are called the commingled composite materials, which are used still a lot, especially in automotive industry. The mesostructure means that means accounting for the difference which is made, keeping all the other parameters the same. If I use, for example, a quill instead of which is the tissue for the wave structure for which is used in jeans, for example, particular type of quill, you might have a plain structure, or you might have a satin structure. So mesostructure means taking into account the difference which is brought by the different kind of weave. Basalt. A little bit of more information about basalt, because it's a new thing, and to compare glass and basalt. In practical terms, the advantage of basalt is that you extract them from the rocks, basically directly from selected rocks, of course. You don't take any basaltic rock, and you can make chopped fibers or needle mat. Basalt was developed, especially in Russia, at the times where asbestos was very popular, which were never made composites of because of the dangerous characteristic. But basalt proved not dangerous, and you can make chopped basalt fibers or needle mats, and all these kind of weaves and nets. In composite, what we did in reality, we exploited the experience into building. In building, they have started using glass fiber composites in the 50s, before the interest for glass fibers, for fiberglass exploded in the other fields. So in practical terms, you have almost the same characteristic. You have less calcium oxide in the case of than in the case of glass. This is the glass, the so-called E glass. This is the composition, the so-called E glass. E glass means the common glass. It's a common glass with less sodium oxide. The glass for window, which is not very strong into tension, has quite a lot of sodium oxide. Here instead we have little sodium oxide, we have still a lot of calcium oxide. There is a stronger, also a stronger glass, which has basically no calcium and sodium oxide, which is the S glass, which I report here to the bottom. The S glass is much more expensive, and the S stands as strong. I don't know if it is their intention, but you may remember it like that. So temperature of service, for example, is quite high for basalt, even higher than for glass. Density, it's a bit higher. You can see here gives you the idea of the properties, and the properties are about the same, with the advantage that the production system of basalt is simpler, because in practical terms they don't need any particular treatment to be adapted for their introduction into composite. The service temperature is theoretical, because in reality, if they are used in composites, the polymer resin has got a service temperature which is much lower. If you use thermoplastic like polypropylene have a service temperature below 200 degrees. Epoxies, which are thermoset, go a bit beyond, but not to these temperatures anyway. So an important characteristic are the two, since basalt and glass are both kind of basic alkaline structures, it is important to verify their resistance into acids, due particularly to application at sea, where you have lots of sodium chloride, and in practical terms, you do this kind of salt fog tests. These are very diffuse into materials. And other tests are done for the introduction of their nets, not only in composite, but also in cement. Please consider that these fibers can be used as also other fibers, as also hemp fibers, less flax fibers, but carbon fibers, of course, that can be used also into building. Carbon fibers, they are not terribly used in buildings because of their cost, but otherwise they would be suitable. They would be suitable. So another test is done with their saturated solution of cement. Let's imagine that cement is attacked by moisture, and in the end it tends to become a kind of powder into water, and we need to see whether they are going to attack either basalt or glass fiber. That's why they do this kind of tests. Anyway, they are not conductive, as it is not the case for carbon. Carbon instead, they are much more conductive, and with carbon fibers, the situation is the same. So fracture. These are micrographs of fracture in glass fiber epoxy composites, and it is important that here you don't see any pull out. There might be a pull out at some time, at some point, but here you don't see them. And it is important that one of the questions which is important to remember is that an interface can form in case that the length of the fiber, despite being short, exceeds a given critical length. So if the length of the fiber exceeds a given critical length, then you are able to say, well, an interface will form. There will be, in other sense, a real improvement. So you don't have a feel that you have a real reinforcement. How do you measure the critical length? Of course, the load which is applied between fiber and matrix, any adhesion load, it's a shear load, a shear stress. So you need to consider the diameter of the fibers, which might be very different. Glass fibers, you get to 25 fibers, 25 microns. In the carbon fibers, much less, you can get as low as 5 microns. Kevlar fibers is in between. And you need to consider that tensile resistance is much more than shear resistance. We might consider that to give an idea about this formula, equation. You will know the fiber's diameter because you fabricated the composite. You will know the tensile strength because you have done tensile stress of the fiber. What it is more difficult is, as for testing, is to measure the shear strength of the interface. The shear strength is much more difficult to measure because tensile fibers are for tensile strength. Just we have seen it for steel. It's the simplest. Simplest, well, it's not cheap, but it's simple in technical terms. It's simple. Okay, and then you can determine the critical length with this formula, and since a shear, well, a kind of rule of the thumb would say that the shear strength is about 10 times less than tensile strength. In practical terms, since the diameter is the one we know, the critical length needs to be at least higher than around 100, 300 microns. So in general terms, well, you can imagine that sigma f and tau c have got that ratio is about 10. The diameter can be around 5 to 25. So it's fair to assume that critical length is some hundreds of microns or some tens of millimeters, as you can. Having said that, an empirical definition says that fibers are continuous where their length exceeds 15 times the critical length, so a few millimeters. So you can say that if you have fibers of a few millimeters, they can be assumed as continuous, and you can imagine, you can apply also in terms of you can apply the rule of Misters as well. You can imagine that the rule of Mister may work for the optimal conditions of fibers, because the rule of Misters assumes that the fibers need to be continuous. Okay, and we are almost at the end of our lecture. I would conclude with the question of finishing. You may have realized that fibers, apart from carbon and basalt fibers, which can be made round section quite easily, other fibers need finishing. Glass fibers need finishing normally with silane, which is a polymer not very far from silicon chemically, and it gives them a smooth appearance. Um, and they become in that way kind of they lose something in terms of the kind of cylindrical, they lose something in terms of tensile strength, but this works because they are cylindrical anyway. Then there are a few methods which are shown here in small for the verification of the fiber matrix interface. In other words, to measure the shear strength, the shear critical strength. And therefore you can do a number of different tests. You can have a micro drop, so a fiber in resin drop. You can have the fragmentation test. The fragmentation tests are also very interesting to measure the critical length. And also the critical lengths beyond which the material behaves as a composite. So the fiber acts as a reinforcement. And you will see it practically because the tensile strength with fibers below the critical length drops. You have values which are at a certain point the values drop because the fibers are no longer in reinforcement. Before doing a tensile test, which are simple yet expensive, you do something much cheaper, which is the microdrop or the fragmentation, the pull out, which are especially very simple tests. So you pull and you have this kind of tests. Okay, and I think we end up with this. Next time we are going to carry on discussing about composites. Then we will have a diversion towards natural fiber composite application in natural fibers. In the understanding that in our course it's both scientific and natural materials together, because now there is no longer the time to do any distinction. We need to use synthetic and natural materials together, even in combination, even in hybridization. We define hybridization not from the chemical point of view. Hybridization in material science means putting together two materials and making a further material which will work as one. So, for example, if you put flax and carbon fibers into a composite, you are making a hybrid composite. After that, we are going to have the last couple of lectures on polymers and biopolymers. And then I'll end the course. As you may understand, it's too short possible to talk about all material science, but I hope I raised your interest. Anyway, let's start thinking on what you want to do, which subject you want to write about. And then we will have an oral once I have approved your article, your script, which might take some time. You will have an oral which will involve especially a discussion about the themes of material science. I will not ask you details about values, because values may always change, but I might ask you what is the sense of having a critical length, what the critical length is about, more than the real value of critical length. Is it other definitions, but more than definition, the operational sense of a definition. Why measure the stiffness of something or the stress intensity factor, or what is the importance of voids into a kind of etc. etc. Okay, so on Monday we won't have lecture because it's San Venanzo in Camerino, and we stick to that. And so we are going to meet again at 11 on next Friday. Meanwhile, have a nice weekend.